All right, new section today is 2.6 continuity. Most of what we've done so far has assumed that we had a continuous function. The outputs can vary continuously with the inputs and do not jump from one value to another without taking the values in between. The limit of a continuous function as x approaches c can be found simply by calculating the value of the function at c. That's where we just plug in or we just find our value. For looking at continuity at a point, here's example 1. Find the points at which the function f is continuous and the points at which function f is discontinuous. Okay, so whenever I look at this, I'm literally looking, where can I go without picking up my pencil? And so, as I come down here to 1, if I'm going to move on to the rest of the graph, I would have to make a jump with my pencil and come back up to here. So my continuity doesn't work there. So this would be discontinuous at x equals 1. Then as I continue along this graph, here at 2, I have an open circle, and then it jumps again up to 2. So it would also be at 2. Coming up to x equals 3. This is continuous because it doesn't jump. And then I come down here, and at 4, when I'm hitting 4, I jump from 1 down to like 1/2. So this would be discontinuous at 4 as well. So where would f be continuous at then? Well, if we look at the graph, f is continuous everywhere between 0 and 1. So we would graph that, or we would mark that interval down, continuous from bracket 0 to 1 parenthesis. Also from 1 to 2. In a 2 we have a jump, so that would get a parenthesis, open circle. And then it's also continuous from 2 to 4. So those are all the different places where it's continuous, and these are the points where it's discontinuous. At 1, x equals 1, 2, and 4. Interior point. A function y equals f of x is continuous at an interior point c of its domain if the limit as x approaches c of the function is equal to f of c. In other words, if I plug the point in, if that gives me my limit, then it is going to be continuous there. At an endpoint, a function y equals f of x is continuous at a left endpoint a or a right endpoint b of its domain if. So if I'm looking at a left endpoint a, then as I approach, the limit as x approaches a from the right, if that's equal to f of a, so if I just plug the point in and my limit approaching from the right is equal to plugging the point in, then that gives me that it's continuous at that endpoint. Or if it's a right endpoint, then my limit as x approaches that right endpoint from the left of the function is equal to just plugging the number into the function. In other words, if I look back at my last one, right? If I'm looking at this endpoint here, okay, I can tell if it's continuous at that point if whenever I plug this point into the function, it gives me the same as my limit as I approach from the right. Why does it have to be from the right? Because there's nothing on the left-hand side of it. So if it's a left endpoint, I just check the limit as it approaches from the right. If it's a right endpoint, I check the limit as it approaches from the left. In this case, if I plug, say, f of 0 in, if I plug 0 into my function, it gives me 1, because that's what my y is when x is 0. If I look at my limit as it approaches from the right, my graph is getting closer and closer to 1. So since my limit is the same, this is continuous at the point 1. Here on this end, if I'm looking at the endpoint 4, if I plug 4 into my function, f of 4, I get this here, which is 1/2. But if I look at my limit as it approaches, it gets closer and closer to 1. So the limit as x approaches 4 from the left equals 1. These two are not the same, so it's not continuous at this point. I can also look at another endpoint here, which shows me an error that I actually made in here. If I'm looking at this endpoint here, where it's stopping at 1, if I plug 1 into my equation, f of x equals 1, I get this point here. I'm sorry, this should be f of 1. Then I get this point here equal to 1. So when I plug my x in, my y is 1. If I take the limit, this is getting closer and closer to 1 because it stays 1. So if I'm looking at my limit as it approaches from the right-hand side, then it's continuous at f of 1. Which means that when I do this interval here, that should be a 1 because it's closed circle. But if a function f is not continuous at a point C, we say that f is discontinuous at C, and C is a point of discontinuity of f. A function f is right continuous, or continuous from the right, at a point x equals c in its domain if the limit as x approaches c from the right of the function equals f of c. That's like this one. This point here was right continuous. Now, is it continuous overall? No, because I have a jump here at 1, but it's right continuous. So if this was an endpoint, it's kind of what we came to last part when I was writing this down. If this was an endpoint, then it would give us a continuous function because it's right continuous. It's left continuous if it's the same direction but opposite. So if I'm taking the limit from the left as x approaches c from the left of the function f, and that's equal to plugging the number in, then I would call this left continuous. A function that's continuous throughout its domain. The function f of x equals the square root of 4 minus x squared is continuous at every point of its domain, including x equals -2, where f is right continuous, and x equals 2, where f is left continuous. So if I'm looking at the square root of 4 minus x squared, this gives us this graph here, and it's continuous across the entire thing. Here at this endpoint x equals 2, it is left continuous because as I'm approaching from the left-hand side, if I plug a 2, it would give me, my limit would give me 0. But if I plug a 2 in here, 4 minus 2 squared also gives me 0. So my limit would equal 0, and if I plug it in, it gives me 0, so it's left continuous. If I'm looking at the point -2, it would be right continuous, because if I take my limit as x approaches -2 of the function, I would get 0. In other words, my graph is getting closer and closer to 0 as x gets closer and closer to -2. Since that's happening, and I plug a -2 in here, 4 minus -2 squared. -2 squared is 4. 4 minus 4 is 0. Square root of 0 is 0. So I get the same thing whether I'm taking the limit or just plugging the point in. That tells me that this one would be right continuous. My left endpoint is right continuous, and my right endpoint is left continuous. So this is continuous across the entire domain from -2 to 2. Our continuity test says that a function f of x is continuous at x equals c if and only if it meets the following three conditions. If f of c exists, which means whenever I plug the number in, then it should give me a function. If I had like 1 over x, and I asked you to find f of 0, that's not going to work, because if I plug 0 in, it does not exist. So it's continuous at the point c only if c lies in the domain of f. In other words, I should be able to come out with an answer. 0 would not lie in this domain, because it would give me an answer that does not exist. So that's the first condition. The second condition is that as the limit of x approaches c of f of x, that has to exist as well. So I have to be able to find a limit of the function as x approaches the point. And lastly, my limit has to be equal to plugging the number into the function. So the limit has to equal the function's value. If any of these three things are not true, then it is not a continuous function. Or at least it's not continuous at that point. So there are multiple types of discontinuities, and I want to walk through some of those right now to finish class. So the first one, this one, is a continuous function. It's continuous at x equals 0, specifically because the point is filled in. So this is continuous at x equals 0. The second one here has an open circle. So at x equals 0, we have nothing. It's undefined. In other words, this would be discontinuous at x equals 0 because of the hole. It would be continuous if f of 0 equals 1, because my limit as I approach from the left is 1, my limit as I approach 0 from the right is 1, and so if I plug 0 in and got 1, then this would be a continuous function. If I look at C, this one is also discontinuous at x equals 0. Oops. And it's really the same thing here, because f of 0 equals 2, and the limit as x approaches 0 of the function equals 1. So my limit here, as I approach from the left and right, is 1. But if I plug the point 0 in, I get 2 because that's where the filled in circle is. These two types, B and C, are called removable discontinuities. Since each function has a limit as x approaches 0, both being 1, I could remove my discontinuity by setting f of 0 equal to that limit and just come out and say, as an add-on to this, f of 0 equals 1. We're not really looking at that yet. I just want to let it be known that these two types, where I have this jump and where I just have a hole, are removable discontinuities. And again, we will get to that later. The next one, those ones are more serious because my limit as x approaches 0 does not exist. So there's no way to remove this. My limit as x approaches 0 of the function f of x does not exist. And the reason for that is, as I approach from the left, my limit is 0. As I approach from the right, my limit is 1. And so this creates a jump discontinuity. Because my whole function jumps. And I think I called this a jump up here, which is not a good terminology to use. Because even though I jump up, it's only at one point. So this is a point discontinuity for both of these. If we were going to call it anything, that's what we would call it. Because there's only one point that doesn't work. So this would be a point discontinuity. Whereas these down here, that's a jump discontinuity. The whole function jumps up one step. Now for this one, there's no way to improve our situation. I mentioned up here, if we set each of our f of zeros equal to something, then we could remove our discontinuity. There's no way to remove this. The one-sided limits do exist, but since they have different values, then it's not going to work. This function down here, as I approach 0 from the left, it goes to infinity. As I approach from the right, it goes to infinity. So our limits for both of these go to infinity. However, it's not going to make it continuous because there's never ever going to be anything at 0. And so this would be called an infinite discontinuity, because even though our limits go to the same thing, there would be, if I could spell, it would be better. Even though our limits go to the same thing, they both go to infinity, there would never be an f of 0 or any way to plug 0 in here. And then this last one here is called an oscillating discontinuity. And that's just because it oscillates too much to have a limit as x approaches 0. We looked at one like this in the last section, or maybe the section before, but it just oscillates too fast to have any limit. And so we can't call this we can't ever find a limit of it. All right, guys, that's enough for today. I'm going to give you some fairly simple homework problems on this, and we will get back to it tomorrow.